Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is to find lower and upper bounds for Ramsey numbers using binomial coefficients. I will remind you what those things are, but you should watch my other videos on Ramsey numbers if you don't know what those are. This would be a pretty quick, even though I will tell you everything, this is probably not the greatest place to start on Ramsey numbers. And you need to know something about binomial coefficients, and I have plenty of videos on those to be able to follow this lecture. Okay, so our goal is to show that the Ramsey number n comma m, which I will tell you what it is in a second, is less than or equal to the binomial coefficient n plus m minus 2 choose n minus 1. So this is an upper bound for Ramsey numbers. So even without doing any kind of work, this will tell you that if you're looking for a Ramsey number, you can limit your search and not go above this number. We'll also show a very weak lower bound that R and M is greater or equal to n minus 1 times n minus 1 plus 1, and a slightly better one, but one that has an interesting way of arguing, something called the probabilistic method, to show that the diagonal Ramsey numbers, R and N, are greater or equal to 2 to n over 2 minus 1/2 minus 2 over n. Actually, the same argument shows that is greater or equal to 2 to the n over 2, and actually better than that. But I will only show the other one. So first of all, let me tell you what Ramsey numbers are. So if we use this notation, ks arrows to kn comma km, and that's a claim. So it says that if you take a complete graph, that means on S vertices, put S vertices and put all the edges among them, and arbitrary color the edges of that using two colors, blue and red. So some of the edges make blue, some of the edges red, and then you are guaranteed that you will have a blue Kn. That means n vertices among those S vertices where all the edges among them are blue, or a red Km, m vertices that all the edges among them is red, or both. Now, this is a claim, could be true, could be false, depending on what S, N, and M are. This may or may not be true. Ramsey's theorem tells us, the subject of a previous video, that if you give me your wish list, your N and M, then there is an S that will make this claim to be true, that there will be an S large enough so that if you start with a KS and color all the edges of a complete graph with S vertices in one of two colors, then you're guaranteed a blue Kn or a red Km. And in fact, the smallest such positive integer that you have this property for is the Ramsey number Rnm. And it's called the Ramsey number. Now, finding these Ramsey numbers is very hard. It's not actually easy to find where the threshold is. What's the S that when your system gets complicated enough, complex enough, when S is larger than that, then you're guaranteed the blue Kn or Km. But we can prove that if you go large enough, and in fact that's what the upper bound is, if you go large enough, this will automatically happen. And we can come up with lower bounds also that tells you that you at least need this many. Now, for those lower and upper bounds are going to bound things, but they're not going to give you the exact number. You'll have to do a lot more work to find exact numbers. Okay, so some known Ramsey numbers, again, subject of previous videos, R336. This is the one that you maybe even be able to argue yourself if you think about it hard enough, but a subject of a previous video that says that if you take 6 vertices, draw all the edges between them, think about 6 people and their friends, and who's friends with who on a social media platform, then you're guaranteed that there are 3 people such that they're all common friends with each other, or 3 contacts with each other, or 3 such that no 2 of them are contacts with each other. And we also proved that R34 is 9, R35 is 14, and R44 is 18. Also, R1M is 1 trivially. If you just have 1 vertex, no matter what you do the coloring, you will have a blue K1, because a blue K1 is just a vertex with no edges, and therefore there's nothing to worry about. And R2M is M. If you have M vertices and color all the edges with 2 colors, if you use blue, then you will have a blue K2. If you don't, you will have a red KM. So those are obvious ones. but many other ones are not known. So R55, for example, the best that's known at this time is that it's between 43 and 48. R66 is between 102 and 161. R46 is between 36 and 40. R610 is between 204 and 949. So these are the best known bounds, and they're not given by the bounds that I'm about to prove. The bounds that I'm about to prove are much worse than these. Well, the upper bounds are not that bad, but the upper bound we're going to find. But the lower bound is definitely much lower than it should be. But these have been found via lots of work, including using computers, although computers alone can't do it. If you think they can just tell a computer, tell them, find me this number, you will be wrong. One of the things we proved in a previous video that was actually how we proved Ramsey's theorem that there is such an S is to show that Rn(m), the Ramsey number with N(m), is less than or equal to Rn minus 1m plus Rn(m) minus 1. And in fact, that's what I'm going to use for the first bound that I want to find. So using this recurrence relation, mind you, this inequality, we can find upper bounds for Rn(m). So as I said, R1m and Rn1 are 1. So if you write these want to write these Ramsey numbers in a table, you know that the top row and the first column is 1s. After that, though, you can use this this relation to find bounds. So because R12 and R21 are less than or equal to 1, then R22 is less than or equal to 2. That we could find it directly ourselves. But the point is that that bound will give you all kinds of bounds that you go along. And this is actually the bounds that we want to prove. This gives you bounds, but we want a formula for them. What are these numbers? And in fact, if you sort of tilt your head and look at this table, you will see that it's what's commonly known as Pascal's triangle and what I like to call the Karaji triangle. These are binomial coefficients. So they're just skewed. So 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. These sort of diagonals, off diagonal, are the rows of the Karaji triangle. And that's what we want to show that's what they are. So N and M are two positive integers. R and M is the two-color Ramsey number. And what we want to prove is that R and M is less than or equal to n plus m minus 2, choose n minus 1. If you figure out which binomial coefficient is in which row, you will get to this. And if you n minus m minus 2, choose n minus 1 doesn't look symmetric enough for n and m, it's really the same as n minus 1 plus m minus 1 factorial divided by n minus 1 factorial times m minus 1 factorial. Now, what's the proof for this? The proof for it that this is actually not that complicated, but the technique needs a little bit of explanation if this is the first time you're seeing it. So it's induction on n plus m. It's not induction on n or m, it's an induction on n plus m. So what does that mean? Well, that means that you start, well, first of all, we know as our base case says, we check R1m. So if n is 1 and you plug it in, you will see that you get m minus 1 choose 0, which is 1 for the formula that we gave, and that's correct. We also check Rn1 as our base case, and that gives you n minus 1 choose n minus 1, which is also 1, which is correct. So we just check those, and then after that, for n and m bigger than 1, then we use we work like this. We say that, okay, we're trying to prove this for one particular combination of n and m. We'll assume that's true whenever n plus m is smaller than the one we're looking at. So that means that the way we're going to go induct and go step by step up is first we'll prove the case n plus m equals 2. Well, that only happens with n and m are 1, so we actually know that already. Then we go to n plus m equals 3. That's the only happens when n is 2 and m is 1, and n is 1, m is 2. But when we're proving that, we can assume that we've already proved the cases where n plus m is 2. Then we go to n plus m equals 4. That gives us 3 cases. N is 3, m is 1, n is 2, m is 2, n is 1, m is 3. And in proving those, we use the fact that we know the result already for n plus m equals 3 and n plus m equals 2, and so on. So n plus m equals 5, that probably is the first place where No. I mean, we actually already know all of those. I was going to say that's the first place where we see something we haven't seen before. But just the trivial things already will tell us. But this illustrates the way we're going to prove this is that we're going to prove it for one particular choice of n and m, but we'll assume that not n or m, but n plus m. If it's smaller, we've already proved it. Okay, so we know this relation. Again, this was the subject of a previous video. This is where the Ramsey argument comes in, that Rnm is less than or equal to Rn minus 1m plus Rn m minus 1. That actually needs an argument to get that, and you need an argument about coloring and monochromatic Kns or Kms to get that. So what we want to prove is that R and M is less than or equal to n plus m minus 2, choose n minus 1. And we know that it's okay if n equals 1 or m equals 1. So for greater than 1, this is our inductive step. We start with saying that, well, okay, R and M, we know that it's less than or equal to Rn minus 1m plus Rn comma m minus 1. Now, for each of those, when we have Rn minus 1m, Rn minus 1 comma m, the sum of these is less than n plus 1. And the same is true there. And so for both of those are prior cases that we have already done, and induction allows us to say that we already know those. And therefore, for the first one, we can, instead of n, put n minus 1, and instead of m, keep it as n, and we get n minus 1 plus m minus 2, choose n minus 1 minus 1. And for the second one, the same thing, but with m's, n plus m minus 1 minus 2 plus n minus 1. And if we simplify these two, we get n plus m minus 3, choose n minus 2, and n plus m minus 3, choose n minus 1. Now we use the identity for binomial coefficients. So n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. That's what allows us to write the binomial coefficients in the Karaji GR triangle, what's known as Pascal's triangle. And so here I have n minus m minus 3 choose n minus 2 plus n minus m, n plus m minus 3 choose n minus 1. So by that identity, this is the same as n plus m minus 2 choose n minus 1. Sometimes instead of n plus m, I said n minus m. I apologize for that. But this is what we wanted to prove. So this follows from the identity for binomial coefficients, as well as what we had proved for Ramsey numbers. Again, watch my previous videos on Ramsey numbers, as well as one on binomial coefficients to see where these things came from. So now we want to look for a lower bound, something that says that, well, a Ramsey number has to be greater or equal to something. And first, we'll come up with a quick but a very weak one. So I'm going to say that the Ramsey number R and M is greater than n minus 1 times m minus 1. So I'm going to let S be this number. And what we're trying to show is that Ks doesn't arrow to Kn comma Km, meaning that you're not guaranteed, like if you start with this many vertices, you're not guaranteed a blue Kn or blue Km. If you start with this vertices and then take the complete graph and color all the edges between them with blue and red, you are not. So how am I going to prove to you that you're not guaranteed? Well, that means I've given you a counter example. I have to show you it's possible to color the edges of Ks using two colors without creating a blue Kn and a blue K and a red Km or a red Km. And the most obvious thing to do is a construction. So come up with an example to show me that. And in this case, we can. So I'm going to, S is n minus 1 times m minus 1. So I'm going to arrange the vertices in a rectangle in n minus 1 rows and m minus 1 columns. And in this diagram, I've showed you the case when n is 3. So there's 2 rows, and m is 4. So there's 3 columns. Then what I'm going to do, so this is going to be my Ks. So I've got to now connect all the edges and color them. So what I'm going to do is that I'm going to color with red any two vertices that are in the same row. So there you go. You color red every 2 vertices that are in the same row, and all the other ones you colored blue. So that means the ones that are in the same column, but also the ones that are sort of diagonal. So everything else is blue. And the claim is that now you do not have a blue Kn or a red Km, and it's easy to see why. if you were going to have a blue Kn, you would need n vertices, but there's n minus 1 rows. So that would mean 2 of the vertices would have to be in the same row, but then they're connected with a red edge. And so you do not have a blue Kn. Also, how would you get a blue red Kn? You would have to have m vertices, but there's m minus 1 columns. And so 2 of the vertices, whatever Km you pick, would have to be in the same column. But if they're in the same column, then their edge is going to be blue, and so we don't have that, and so we're done. But again, this is a pretty weak one. Now, the next lower bound I'm going to give you is much better, although it's not that good, but it's much better. But this is actually a proof of concept that you can actually prove lower bounds without actually constructing an example. So. And the theorem is said in a weird way, but we will later make it look a little bit better. But this is actually sort of a good way of saying it. So assume that you have an integer n, and you're trying to find, and this lower bound I'm just going to give you for, you can do it for general R and M, but I'm going to give you for the diagonal Ramsey numbers R and N. So pick your n, and then assume that you found an S such that S choose n is less than 2 raised to the power n choose 2 minus 1. Where did that come from? Well, that came from the proof. And then the claim is that R and N is going to be bigger than S. So that's what we're going to try to prove. So first, let's just see what this means. So if n is 5, then n choose 2 is 10, and 2 to the 9 is 512. So this says that you need an S such that S choose 5 is less than 512. And because this is a lower bound, you like bigger S's. You don't like small S's. Now, 11 choose 5 is 462, but 12 choose 5 is 792, is already bigger than 512. So our result will say that R55 is greater than 11. So this result, that's what it will tell us about R55. Is that any good? No, our earlier bound, the one I kept calling weak, actually in this case was stronger. It gave us 5 minus 1 times 5 minus 1, which is 16. So that did even better. But neither one is really that good, because what we actually know, although through a lot of work, is that this diagonal number R55, this Ramsey number, is greater or equal to 43. Now, if the n is bigger, then this new bound is going to do better. So for example, if n is 10, then using this, you will see that you have to calculate, and you need a pretty good calculator, or not a calculator won't do, like some kind of a symbolic thing that will allow you to show you that this thing R1010 is greater than 100, and the earlier bound was that R1010 is greater than 81. That the weak one was 9 times 9, 81, and 100 is better than that. Although what's known is that R1010 is greater or equal to 798. Now, if you go to n equals 31, then this, what I'm calling a probabilistic bound, gives us that R3131 is greater than 397,913. The weak one, the one we did before, would say 30 times 30, 900. So now this does a lot better than the other guy. So this guy leaves that other bound in the dust when we get here. I actually don't know what we know about R3131. This theorem can be made better than that, and people have done that, but I haven't done my homework to find out what's the best known for R3131. So the point of all of these different ones that I showed you is that these bounds are not particularly necessarily good, like in the sense like they close down and tell you precisely what RNN does, but they're better than nothing. And actually, this last one it's not a bad one as a lower bound goes. It's something, and it's a proof of concept. In fact, the argument that I'm going to make, it's so like you will see that you should be able to do better than that, definitely, and people have done that. This is an existence proof. It's not constructive, and it's due to Erdős from 1947. And usually it's presented using the language of probabilities. And in fact, this is probably one of the first, maybe the first, use of probabilistic methods in finite combinatorics. And that field has grown and become a major part of what combinatorics do now using probabilistic methods. But at least in these simple cases, it's really just counting. Probabilities in the case of finite sample spaces is really just counting. And I'm going to present it as a counting problem. Now, in more complicated situations, you might want to use the language of probabilities because you might be able to use some of inequalities that come from probability theory. However, in this case, it's just a basic counting. So, proof of this lower bound. So what is it that I want to prove? I'm assuming that I have an n and an s, and s choose n is less than 2 to choose n choose 2 minus 1, and I want to show that r and n is greater than s. That's the claim, and that's the same as showing that if you have that many vertices s, and you make the complete graph on s vertices, color all the edges with two colors, blue and red, you will not get a blue kn or a red kn. You don't get a monochromatic kn. So I'm going to say, okay, this is the way we're going to do it. Color your edges of ks any way you want with blue and red. I'm not going to tell you color it in this particular way, and then you're not going to get it. I'm just going to say color it in any way you like. And I'm going to ask, how many ways can you do that? How many ways are there possible to color the edges of ks using blue and red? Well, for every edge, you have two choices, blue or red. After you do that, this other edge, you have two choices, blue and red. So 2 times 2 times 2 times 2, as many as their edges. How many edges does ks has? S choose 2. So the total number of possibilities, so total number of ways of coloring a ks, the edges of ks with blue and red, is 2 raised to the power s choose 2. Now, I want to know how many of these I don't like. The ones I don't like in this case are the ones that do give me a monochromatic kn. And I want to sort of roughly estimate that. Finding this exactly is very hard. But estimating is not that hard. So this is what I'm going to, well, if you want to have good estimate, it would be hard. But if you want a sloppy estimate, then it's not that bad. So this is the way I'm going to say. So if you want to color the edges of ks with two colors in a way that you get a monochromatic kn, well, this is what you should do. You should pick a kn, pick n vertices, then pick a color, and then color that kn, the edges of that kn with that color, and then color the rest. Then color the rest any way you want, and you guaranteed your monochromatic kn. Well, how many ways can you do these steps that I just outlined? Well, picking a kn, so you have to pick n vertices out of the s, so that's s choose n. Then you pick a color. You have two colors, so you have two ways of doing that. Then you have to color that kn using that color. Well, that you don't have any choices. You just have to color them. And then coloring the rest, that means every other edge, you have two choices for them, red or blue, blue or red, blue or red. So it depends on how many edges are left. And the number of edges left is s choose 2, the total number of edges in ks, minus n choose 2, the total edges in the kn that you already colored. So this is what B is. Now, is this really the number of ways that to color ks and get a monochromatic kn? Absolutely not. This is a way overcount in the sense that there are many ks's that have not just one kn, but many different kns that are monochromatic. And we have counted those many times over. So we have an overcount. And so this is a lot more than this number that we found is much more than actually the number of ways that you can color ks and get a monochromatic kn. But if this B, as large as it is, still less than A was the total number of ways that you color ks. If B is still less than A, then you're assured that there got to be some that don't have monochromatic kns in them, and therefore ks doesn't arrow to kn comma kn because there got to be some there. Okay, and what's this B? Well, B is s choose n, and then if you put those things together, is s choose 2 minus n choose 2 plus 1. But s choose n, we had assumed that it's less than 2 to the n choose 2 minus 1, and that was sort of rigged for this proof to work. So if you put that there, we get less than, this is going to be less than, instead of s choose n, I put 2 choose n choose 2 minus 1, and then bases are the same, you add the exponents, and you get 2 choose s choose 2, which is A. So B is less than A. Even though we did that huge overcount, it's less than A. So if it's less than A, there got to be some colorings of KS that do not have any monochromatic guys in them. So KS can't possibly arrow to KN comma KN. These probabilistic arguments can't be that precise. I mean, you can make them a lot more precise than this, but you're not really saying. I mean, you're not really getting to the case where, well, here's how you color it, and look, you're right at the threshold, and then so you have to be really careful how you color things, otherwise this don't work. It says that if you have this big of a KS, if you randomly do it, the probability of getting one where it has no monochromatic KNs is greater than 0. That's basically what we proved. But when you say this in the language of probabilities, that's how you say it. We can simplify this lower bound, although weaken it a little bit. So we proved that if S choose n is less than 2 to n choose 2 minus 1, then R and n is greater than S. So by estimating this, we can simplify, estimating S choose n, we can simplify the result and also weaken it. But it'll look a little bit better. With a bit of care, you can get that R and n is always greater than 2 choose n over 2. I'll do a more sloppy estimate that will actually give us something very close to 2 raised to the power n over 2. So this is what I'm going to do. S choose n, what is that? Well, that's S times S minus 1 times S minus n plus 1 divided by n factorial, where it's S factorial divided by n factorial times S minus n factorial. But if you take the S minus n factorial and cancel those terms with the corresponding ones at the top, this is what you get. Then I'm going to say, look at the top. You have S times S minus 1. Well, you have the S. Well, that's fine. S minus 1 is less than S. S minus 2 is less than S. S minus n plus 1 is less than S. So all of this is less than S times S times S times S over n factorial. And that's less than S to the n. I'm going to actually even just ignore that n factorial. If you have S to the n pizzas, are you better off just taking them all yourself or dividing up among n factorial people? Of course, you're better off if you just eat it. Take all the S to the n yourself. So S to the n is certainly greater than S to the n over n factorial. So I'm going to use the fact that S choose n is less than S to the n. And then if, now I'm going to just make this number up, if S happens to be less than 2 to the 1 over n, n choose 2 minus 1 over n. How did I come up with that? Well, the proof of the pudding is in the eating. I did the calculations, and this is what I needed. Well, then Sn, well, we have to raise this guy to the nth power. Power of power, you multiply, and those n's cancel, and you get 2 to the n choose 2 minus 1, which is what we wanted. So if S is less than this guy, then we're assured that R and n is greater than S. And what is that guy a little bit? Well, the exponent of 2 was 1 over n choose 2 minus 1 over n, and the 1 over n choose 2 is n minus 1 over 2, or n over 2 minus 1/2. So the corollary is that, well, R and n was supposed to be greater than S, and so as long as S is less than this number, we're okay. So R and n is greater than 2 to n over 2 minus 1/2 minus 1 over n. And for n greater or equal to 3, when you always have to watch out what happens when things are very small. And this is very similar to that 2 to the n over 2. I'm subtracting a little bit more. That makes it a little bit weaker, but not that much weaker. So this is the end of this video. There are other videos of interest. You could subscribe and like if you want to subject yourself to more videos like this to get notifications when they come out. But I have a video on what's Ramsey theory, where we, for example, prove R33 is 6. Then we have the proof of Ramsey's theorem for 2 colors. That's a different video. I have a video on small Ramsey numbers where we prove that R34 is 9, R35 is 14, and R44 is 18. This one was Ramsey number bounds. And there hopefully will be other ones on multicolor Ramsey numbers, graph Ramsey numbers, and Ramsey's theorem for hypergraphs. See you in the next lecture. And again, if you want to subject yourself to more videos like this, subscribe.